We're looking at section 11.3. We're going to be solving simple radical equations in one variable and then give examples showing how extraneous solutions may arise. So if we want to solve a square root or 1/2 power equations, so a radical equation contains a variable within a radical or a variable raised to a non-integer rational power. To solve a square root equation, or equivalently, an equation involving the power 1/2, you can square both sides of the equation and solve the resulting equation. Because opposite numbers have the same square, squaring both sides of an equation may introduce an apparent solution that is not an actual solution, so it will be an extraneous solution. For example, while the only solution of x equals 2 is 2, the equation that is the square of each side, x squared equals 4, has two solutions, -2 and +2. But -2 is not a solution of the original equation. So that's one thing to be aware of when we solve the square root equations. They might introduce an extraneous solution. So we have to check your answer in the original problem to make sure they work in the original problem. So we have the equation 2 plus the square root of x plus 10 is equal to x. The first thing you need to do is isolate the radical, isolate the square root. So move that 2 to the other side. Now you've got the square root term by itself. You can square both sides of the equation. Squaring the square roots, those are inverse functions, so they're going to go away. We're just left with x plus 10 on the left. And then simplifying that x minus 2 squared, you get x squared minus 4x plus 4. So since you got that x squared term, you've got a quadratic. Our normal thing that we want to do is to solve that quadratic, move everything to one side of the equation, set it equal to 0, and then solve from there. See if we can factor. And if you can't factor, then typically we use the quadratic formula. So in this case, it does factor to x minus 6, x plus 1. So that gives us solutions of x equals 6 and x equals -1. Now, since we do have the two solutions, you do want to check to see if either of them is extraneous. So you go back to the original problem and plug in your values. So the original problem, plug in 6. You'll notice we follow the process. We end up with 6 equaling 6, so that's good. That one works. Going back to the original problem and plugging in -1, you'll end up with something that says 5 is equal to -1. Well, that can't be true. So that means that x equals -1 is not a real solution. So we only have the one solution of x equals 6. So first thing we want to do here is rewrite our equation with radicals. So once we do that, we want to isolate the radicals on each side. So in this case, we'll add that square root of 2x minus 4 to the other side. So now we can square both sides since we've got a radical on both sides. Squaring that on both sides is going to just leave us with what is under our radical. So we'll have x plus 6 is equal to 2x minus 4. And then we can solve for x. So subtract the x and add the 4. We get that x is equal to 10. Now typically if you're just getting one solution, you probably don't need to check. It's when we have two solutions that we might have an extraneous, but when in doubt, may as well check it. So we have the square root of 10 plus 6, which becomes the square root of 16, minus the square root of 2 times 10 minus 4. So 2 times 10 is 20. 20 minus 4 is 16. So we're subtracting the square root of 16. So square root of 16 minus square root of 16 will get us to 0. So that means our solution works. It works in our check. So our solution is x equals 10. So thinking back to that problem from part A where we had the two solutions, we've graphed each side of the equation on the graphing calculator. So how can you tell from the graph that one of the two solutions you found algebraically is extraneous? Well, if you look at the graph, there's only one point of intersection. And it's happening at x equals 6. So this is a throwback to what does it mean to, if you have like a system of equations or a solution to something, it's where they intersect. So since these two lines or graphs only intersect at one point, that means you're only going to have one solution, one spot where they are equal to each other. So first thing we want to do to solve this problem, rewrite our power in terms of a square root. So we'll have square root of x plus 5 minus 2 equals 1. Then we want to isolate that square root, so we'll have to add that 2 to the other side. So 1 plus 2 is equal to 3. Once we've done this, we can square both sides of the equation. So we'll be left with x plus 5 on the left. 3 squared is 9 on the right. Subtract the 5, you get x equals 4. Now again, since we have one solution, we probably don't need to check it. So we have two solutions that you run into possibility for extraneous, but we'll check it just to be sure. So going back to the original problem, that's right here. We'll rewrite it. We'll have 4 plus 5 minus 2 is equal to 1. That's the square root of 9 minus 2 is equal to 1, which is 3 minus 2. We get 1 equals 1. So that's a true statement. We're good. That solution works. X equals 4. For solving cube roots, essentially we're doing the exact same thing, except instead of squaring both sides, we cube both sides. So we can solve radical equations that involves roots other than square roots by raising both sides to the index. That's the number of the root of the radical. So to solve a cube root equation, we can cube both sides of the equation. So that's what they did here. Isolate the radical, isolate the root, cube both sides, and then solve for x. So we're going to do the same thing here. The radical is already isolated, so we can just cube both sides. Our left, we're going to be left with x minus 5. Now notice we're taking x plus 1 cubed. So again, there's two different ways you can do it. If you want to take the time to do it out the long way, you can do x plus 1 times x plus 1 times x plus 1. Do this product first and then multiply by the x plus 1. Or if you remember and know how to use it, you could use Pascal's triangle. That's what I tend to do because I know a little bit better how it works than probably most of you. But Pascal's triangle, if you want for the cubed, the coefficients are 1, 3, 3, and 1. This ends up being x cubed plus 3x squared plus 3x plus 1. So when we want to simplify, again, we want to move everything to one side of the equation, set it equal to 0. So we'll get x cubed plus 3x squared. Subtracting the x, we get plus 2x, and then adding the 5, we get plus 6. So we've got x cubed, we've got something with 4 terms. You want to check and try to do factor by grouping. So in this case, we can pull out an x squared, we're left with x plus 3, and then on the right side here, we can factor out a 2, and we're left with x plus 3. That's good for us. So we can now regroup, taking the two factors, the two terms you pulled out and combining them, x squared plus 2, and then x plus 3. So we can now separate this product. We'll get x squared plus 2 is equal to 0, and x plus 3 is equal to 0. If you tried to set those equal to 0, the x squared plus 2 equal to 0, you'd end up with x squared equals negative 2. Well, something squared can't equal a negative, so that means our only solution will be x is equal to negative 3 will be our only solution that works there. So example 1 shows checking for extraneous solutions while example 2 does not. While it's always wise to check your answers, can a cubic equation have an extraneous solution? So the answer here is no. Cube roots only have one solution while square roots have 2. So we won't run into that problem with a cube root. Cube roots only have one solution, while square roots have 2. And that's also true for any even power versus an odd power. So a cube root, a fifth root, a seventh root, those can only have one solution, whereas a square root, fourth root, sixth root, anything with an even power will have 2 solutions. So let's say we want to solve this problem here. So the first thing we want to do is rewrite it in terms of a root. So we have got the cube root here of x minus 50 is equal to negative 10. So we want to isolate this cube root, so we'll need to divide both sides by that 2. So negative 10 divided by 2 is negative 5. From here, we can cube both sides. Negative 5 cubed is negative 125. Add the 50, x is equal to negative 75.